Welcome back everyone to today's lecture, a continuation of the former lectures on potentiometry, which is a key technique in pharmaceutical analysis. This method we are going to discuss in indicator electrode. Let's give a recap on the potentiometry. Potentiometry is a technique in pharmaceutical analysis which allows us to determine the concentration of a solute in a solution by measuring the potential difference between two electrodes. I've guided you through the principles and the equipment. Then a part of the equipment we're going to use is the indicator electrode. And we're going to talk about here the application of potentiometry. Let's dive into we've talked about the reference electrode. Now we're going to talk about the indicator electrode. Here is an overview of what we will learn today, we will cover today. We're going to discuss indicator electrode as well as the metal electrode, the glass electrode, each of which plays a crucial role in potentiometry and the application of potentiometry in pharmaceutical analysis. Indicator electrode responds to the concentration of analyte in solution. By the name implies, indicator, it indicates. There are potential changes based on the ion concentration, making them essential for determining the analyte concentration in potentiometric analysis. Indicator electrode is used to measure the potential of the analyte solution comparing with that of the reference electrode. Its potential is directly proportional to the ion concentration. For example, hydrogen electrode, glass electrode, there's antimony oxide electrode, and there are two types of indicator electrode, the metal indicator electrode and the ion selective indicator electrode. Metal electrodes such as platinum or gold develop potential in response to redox reactions at their surfaces. These electrodes are often used in potentiometric measurements due to their ability to transfer electrons sufficiently. Metal electrodes develop electric potential in response to a redox reaction on the metal surface. Platinum or gold are used as the metal indicator electrodes. These are very similar indicator electrodes. The main disadvantage is that they are not very selective. There are three main types of these electrodes used in potentiometry, but we will discuss only two. We will discuss the first order electrode and the second order electrode. The first order electrode or electrode of the first kind, such as silver electrode immersed in silver nitrate, they develop potential based on the metal's interaction with its ion. These electrodes are straightforward but less selective compared to other types of electrodes. As I said, they are composed of metal. They are composed of metal rod immersed in its own metal solution, as you can see in the diagram. These electrons respond to ionic activity of the electrode. For example, silver electrodes dipped in silver nitrate, as you can see in the diagram. Copper electrode dipped in copper sulfate solution. Second order electrode or electrode of the second kind. They are composed of metal wires coated with salt precipitate. These electrodes are used to measure activity of ions in a solution, particularly in complexometric titration. The electrodes respond to changes in the ionic activity through the formation of complex. This category will include silver coated with a thin deposit of silver chloride or mercury with mercurous chloride. The electrode of this type can be used for direct determination of the activity of metal ions or the anions used in coating. Metallic indicator, while useful, are not highly selective and can respond to other cations besides their own. Additionally, they are limited to use in neutral or basic solution, as they can dissolve in acidic solution, in acidic condition. The ion selective electrode or the membrane electrode, membrane indicator electrodes, have a membrane that is selectively permeable to specific ions. These electrodes offer high sensitivity and are widely used for measuring ions like hydrogen, sodium, potassium in various samples. The ion selective indicator are composed of ion selective membrane by which the ion crosses and it creates the imbalance. Then this opposes the further movement of the ions. Example, glass membrane electrode, antimony oxide electrode. In the glass membrane electrode, this is mostly commonly used in this is the mostly commonly used ion selective electrode. It responds to the change in the concentration of the hydrogen ions. This is composed of glass tube with a thin glass bulb in which the silver chloride wire is immersed in it. Lower part of the bulb consists of 0.1 normal of HCl. This overall setup is immersed in the solution whose potential is to be measured. The glass electrode, most commonly used for pH measurement, is an ion selective electrode. It has a thin glass membrane that is sensitive to hydrogen ions. This makes it highly effective and for accurate pH measurement across a wide range of conditions. First, for the electrode to become operative, it must be soaked in water. During this process, the outer surface of the membrane is coated with a hydrogel which has sodium in it. The metal cation in hydrogel diffuses out of the glass and into the solution, while the hydrogen ion from the solution can diffuse into the hydrogel. The hydrogen ion does not cross through the glass membrane of the pH electrode. It is the sodium electrode that crosses and leads to a change in energy. When an ion diffuses from a region of activity to another region of activity, there is an energy change, and this is what a pH meter measures. It is the hydrogel that makes the pH electrode an ion selective electrode. If external concentration of hydrogen ion is high and the internal hydrogen ion concentration is low, then is lower than is low, then the pH is greater or less than 7. But if the external concentration of the hydrogen ion is low and the internal hydrogen ion concentration is high, then the pH is greater than 7. If external concentration of the hydrogen ion is equal to the external, then the pH is equal. As you can see, this is the glass membrane, the glass electrode composition, which consists of a thin, specially formulated glass membrane. This membrane responds to hydrogen ions concentration by developing a potential, which is then measured relative to the reference electrode. The composition of the glass is crucial as it affects the electrode's selectivity and sensitivity. The pH metric titration is common application of the glass electrode. During this process, the pH of the solution is measured as a titrant is added. The point at which the pH changes most rapidly indicates the equivalence point of the titration, allowing for the determination of the analyte concentration. Let's break down the properties and characteristics of the glass membrane electrode and the antimony oxide electrode. The glass, when we say for the glass electrode, they say the potential is not affected by oxidizing and reducing agent. Well, the glass membrane electrode, particularly the pH electrode, are designed to measure the hydrogen ion concentration in a solution. The potential they develop is a function of the pH of the solution and is not affected or influenced by oxidizing or reducing agent, making them stable in various chemical environment. The one they say they operate on very low pH range, wide pH range. Well, the glass electrode can function over broad range of pH, typically from 0 to 14, allowing them to measure both acidic and basic solutions effectively. They respond fast and functions well in psychological system. Well, they provide rapid and accurate responses, which is crucial for application like psychological measurement, where quick results are needed. They are very selective. Well, glass membrane electrodes are highly selective for hydrogen ions and are less affected by the presence of other ions in a solution, which helps in accurate pH measurement. With proper management, proper maintenance, glass electrodes can have a long operational life, making them have long lifespan. They are generally durable, though they need to be stored and handled carefully to avoid damage. The antimony electrode, talking about the antimony electrode, well, the stability. It's well known for its stability, the antimony oxide electrode. When an antimony rod is dipped in a sample solution and exposed to air, it forms a stable antimony oxide layer on its surface. This stable layer helps maintain consistent electrode performance. It also cannot be used in the presence of dissolved oxygen or oxidizing agent. This primary disadvantage of its electrode is it's susceptible to interference. It has susceptibility to interference with dissolved oxygen or oxidizing agent. This substance can react with the antimony oxide, affecting the electrode's performance and accuracy. The reaction at the antimony oxide, antimony reacts with water to form antimony oxide. The hydrogen ions and hydrogen ions. This reaction is central to the electrode's ability to measure potential difference. Well, in summary, before we dive into the next topic, the glass membrane electrode is ideal for measuring pH due to its wide range pH, fast response selectivity, stability against redox reaction, while the antimony oxide is known for its stability but limited by its sensitivity to oxidizing agent and dissolved oxygen. It forms a stable antimony oxide layer, which is a key to its performance, but also introduces limitation in certain environment. Both electrodes have specific applications where they excel, and choosing between them depends on the requirement of the measurement, including the chemical nature of the sample and the environmental condition. Potentiometric titration is similar to pH metric titration, but involves measuring the potential difference rather than pH. The equivalence point is determined by observing a sharp change in potential, which corresponds to the completion of the reaction between the analytes and the titrant. In potentiometric titration, the endpoint is determined by the sudden change in the potential by the addition of the titrant to the sample solution. This is mainly due to the change in the concentration or ion activity in the sample solution. A simple apparatus is required for simple potentiometric titration, which is composed of the reference electrode, indicator electrode, and their mechanical stirrer. The endpoint is indicated by a rapid change in the potential. Now, to measure the electromotive force of the electrode, system is measured by the potentiometer or by the electronic voltmeter. The methods for determining the endpoint by potentiometric titration are as follows: the normal titration curve, the first derivative curve, and the second derivative curve. This slide shows a typical potentiometric titration curve. As you can see, the potential remains relatively stable until near the equivalence point, where it changes abruptly. The inflection point on the curve corresponds to the equivalence point, helping us determine the concentration of the analyte. If the ingredient being determined produces an electric potential with a suitable indicator electrode, the titration may be followed by the fall in potential as the ingredient is used up. This is a relatively small fall in potential with addition of titrant. As titration proceeds, there is a large fall in potential with addition of the same volume of titrant. In the endpoint region, there will be a much larger fall in potential with a very small volume of titrant. After the endpoint, the fall in potential continues again with addition of titrant if the potential of the sample being determined is plotted against the volume of titrant added to produce a graph. Such a graph is termed as titration curve. A titration curve is a graphical representation of the change in concentration of a particular ion or compound in a solution as a titrant is added during a titration. Like I said earlier from that slide, that titration curve. The curve typically plots the potential or the pH for the pH metric of the solution versus the volume of the titrant added. Here is how you would prepare and analyze a titration curve, particularly in the context of potentiometry. We can calculate it theoretically using the Nast equation, where the potential developed after addition of the certain amount of titrant can be calculated by Nast equation here. Then we can calculate where E is the measured potential, E naught is the standard potential, N is the number of electron transfer in the reaction. The calculated potential after different volumes of the titrant are recorded, and the titration curve can be constructed. And the second one is the experiment in the laboratory. The second is the laboratory experiment. Now, to prepare a titration curve using the laboratory experiment, a typical potentiometric cell consists of two electrodes, the reference electrode and the indicator electrode. Now, let me explain in detail. Please pay attention how you set up the titration. Now, first, we select the appropriate electrode. We use an appropriate reference electrode, e.g. silver to silver chloride electrode, and an indicator electrode, for instance, example, the glass pH electrode or a specific ion selective electrode that are suitable for detecting the analyte or the ion of interest. Then we prepare the analyzed solution. By preparing, we measure a known volume of the analyzed solution and place it in the titration vessel. This solution contains the species whose concentration you want to determine. Now then we choose a suitable titrant. That is, the titrant, we select a titrant which a solution of a known concentration that will react completely with the analyte in solution. The choice of titrant depends on the type of reaction, be it acid, base, redox, precipitation, and so on. The type of the reaction that is to be monitored. Then we begin titration. The initial reading. Before adding any titrant, measure and record initial potential or the pH of the analyte solution. This provides the starting point of the titration curve. Incrementation, addition of titrant. Now you add the titrant to the analyte solution in small and measure the increment. After each addition, allow the solution to equilibrate. Then measure and record the potential. Continue adding the titrant until the reaction is complete, which is typically means the potential no longer changes significantly with addition of the titrant. You continue adding on the titrant until the reaction is complete, meaning there will be no change in the significant change with the addition. There is no significant change of potential in when you add the titrant. Then here you plot titration curve. The x-axis is the volume of the titrant added. On the horizontal axis, you plot the cumulative volume of the titrant added in milliliters. That the y-axis, then the y-axis is the vertical axis. You plot corresponding measured potential in volts or millivolts or the pH. Then you analyze the titration curve. You shape the curve. The shape of the titration curve depends on the type of titration. The strong acid, strong base titration, the curve typically has a steep, nearly vertical rise near the equivalence point, followed by a more gradual slope. The weak acid, strong base titration, the curve has a more gradual rise with a less sharp equivalence point and the buffer region where the solution resists changes in the pH is more pronounced. While in redox titration, the curve might show distinct steps corresponding to the oxidation and reduction of different species. The equivalence point is where the amount of titrant added is equivalent to the amount of analyte in the solution. It is often indicated by a sharp change in the slope of the curve. The potential at this point can be used to calculate the concentration of the analyte. The half equivalence point, this occurs when half the amount of titrant needed to reach the equivalence point has been added. At this point, for acid-base titration, the pH is equal to the pKa of the weak acid. Titration curve is a powerful tool in analytical chemistry, providing insight into knowing the concentration of the analyte and the strength of acid or base involved. The proper preparation and careful plotting of the titration curve allow for precise determination of the equivalence point and other critical parameters in the analysis. There are some key considerations when doing the titration. The titrant addition rate. You have to add the titrant slowly, especially near the expected equivalence point, to obtain accurate data point and a clear curve. The temperature also. You have to maintain constant temperature during titration as fluctuation of temperature can affect the potential reading. The calibration of the electrode. We should have to make sure the electrode are properly calibrated before starting the titration to ensure accurate measurement. The equivalence point or the endpoint detection is a potentiometric titration. In potentiometric titration is the sharp rise or fall in the potential indicated by the indicator electrode. If the sharp rise or fall is sufficiently steep, then midpoint in the steepy portion of the curve is selected to determine the endpoint, as you can see in the diagram. A normal titration curve refers to the typical graph that is obtained when plotting the measured potential against the volume of titrant added. Here is an explanation of a typical acid-base titration. The normal titration curve is fundamental in determining the concentration of an unknown solution. By analyzing the curve, specifically the equivalence point, one can calculate the amount of titrant required to neutralize the analyte, leading to determination of its concentration in the original sample. Values of EMF are recorded after addition of each volume of titrant. The graph is plotted between the volume of titrant against the volume of the EMF or pH. At the end point, there is a sharp increase in potential, or there is a maximum slope of the curve, as you can see in the diagram. Generally, an S shape is obtained. For example, a weak acid and a strong base. This is the normal titration, as you can see. In potentiometry, the first derivative curve is used to analyze the response of an electrochemical sensor, like a pH electrode or ion selective electrode, to changes in the concentration of an analyte. Here is a breakdown of how the first derivative is applied. During potentiometric titration, the first derivative curve can help identify the equivalence point. In this titration, the electrode potential is plotted against the volume of titrant added. The resulting curve shows how the electrode potential changes with the addition of the titrant. The first derivative of this curve reveals the rate of change of the potential with respect to the volume of the titrant added. The point where the first derivative reaches a maximum or minimum correspond to the equivalence point of the titration, indicating the amount of titrant needed to completely react with the analyte. In potentiometric analysis, the first derivative curve can also be useful for calibration purposes. Now, when you are to plot E versus concentration, first you plot the electrode potential against the concentration of the analyte. The first derivative, to get the derivative curve, the first derivative of this calibration curve, dE over dC versus concentration, can help improve the precision of the calibration, especially in regions where the potential changes more rapidly with the concentration. The first derivative curve is particularly useful in detecting endpoints in titration, where changes in potential are small and gradual, making it difficult to pinpoint the exact endpoint using the E versus volume. It enhances the accuracy of the potentiometric measurement by providing a clear picture of where significant changes occur in the response, which can be crucial for analyzing complex samples. Well, the first derivative enhances the precision and clarity of the results by highlighting critical points of change in the electrochemical response. The second derivative in potentiometry can be a powerful tool also for analyzing electrochemical data. It is particularly useful for identifying subtle changes and inflection points that may not be apparent from the first derivative alone. Here's how it works and where it is typically applied. Now, in potentiometric titration, the second derivative curve helps in precisely locating the equivalence point and understanding the shape of the titration curve. By plotting it E versus E, starting with the basic potentiometric titration curve, where the electrode potential E is plotted against the volume of the titrant added. When you compute the first derivative of this curve to identify the inflection point where the potential changes most rapidly, then you compute the second derivative. The point where the second derivative reaches a maximum or minimum indicates the equivalence point more clearly than the first derivative alone. This is because the second derivative highlights points of inflection in the potential change curve. When we talk about calibration and analysis, the second derivative can also enhance interpretation of calibration curve. You create a calibration curve with electrode potential plotted against concentration of the analyte. While the first derivative, you compute the first derivative to get a clearer view of the rate of change in potential with concentration. The second derivative, you compute the second derivative to identify inflection point, which can provide more accurate information about the region where the sensor's response is most sensitive to change in the concentration. The second derivative is particularly useful in complex titration or when dealing with mixture. It provides a more distinct indication of the endpoint by highlighting sharp changes in the titration curve. In case where the first derivative may not clearly distinguish different components or subtle changes, the second derivative can offer additional insights. It enhances the resolution of the data, making it easier to differentiate between closely spaced features or detect minor changes in the system being studied. Let's dive into the advantages of endpoint detection by potentiometry over normal visual indicator. Here are some key points. Now, when we talk about precision and accuracy, the quantitative measurement. In quantitative measurement, potentiometric detection provides precise quantitative measurement of the endpoint based on the electrochemical response, which can be more accurate than visual indicators, which are often qualitative and subject to interpretation. Potentiometric eliminates the subjective nature of visual endpoint detection, which can be affected by factors like observer's perception and lighting condition. Second, the detection of subtle changes. Potentiometric method can detect subtle changes in electrode potential that might not be visible with traditional electrode. This is particularly useful in titrations where the change in concentration is small or gradual. It enhances resolution. The use of first and second derivative curve in potential can enhance the resolution of the endpoint, making it easier to pinpoint the exact point of equivalence. Number 3, applicability of complex system. Potentiometry can be used effectively in complex samples or mixture where visual indicators may not work well or may be confusing due to overlapping color changes or interference. These potentiometric methods can be applied to a wide range of analytes and conditions, including those that do not have suitable visual indicator. Number 4, automation and reproducibility. Automation. The potentiometric measurements can be easily automated using electronic sensors and data acquisition system, allowing for high throughput and consistent result without manual intervention. Automated potentiometric system provide reproducible results, minimizing human error and variability in the endpoint detection. One would say there is no need for indicator reagent. Potentiometry does not require the use of indicator reagent, which can sometimes interfere with the reaction or introduce errors. This makes potentiometric titration cleaner and more straightforward. It reduces the need for purchasing and preparing indicator solution, potentiometry lowering cost and simplifying the experiment setup. One will talk about applicability to visible reaction. For reactions where no visible color change occur, potentiometry is invaluable as it relies on changes in electrode potential rather than visual changes. While potentiometry, in summary, potentiometry provides several advantages over visual indicator methods, including greater precision and sensitivity and applicability to complex systems. It offers a more objective and reproducible approach to the endpoint detection, which can be particularly beneficial in high precision and automated analytical environment. Some of the key advantages of potentiometry include high precision, minimal sample preparation, the ability to analyze both colored and turbid solutions. Moreover, it can be automated, which is beneficial for routine analysis in an industrial setting. It is applicable to dilute solutions. On the downsides, potentiometry requires careful calibration and maintenance of electrodes to ensure accuracy. Some electrodes can be fragile or sensitive to fouling, and the method may not be suitable for very low or high concentration of analyte. Potentiometry has a wide range of applications, including the determination of pH, concentration of ions like fluoride and chloride, and the endpoint detection in titration. It's a fundamental tool in pharmaceutical analysis and environmental testing and clinical laboratories. Thank you for watching. I hope you understand the lectures.